morning, Sanjay.
Good morning.
Very good morning. So we are about to have your second lecture this morning.
Yeah.
Do you want to test your screen sharing, Sanjay?
Yeah, let me check. I'm just thinking whether the board work can be done something on this one, cam board or something.
Yeah, Satish and Arun, you can admit people who are there in the waiting room because we will be starting the lecture in a few minutes.
Okay, sir, I'll accept all this.
Do you want to test your?
Is it?
Yeah, I think it's good.
Yeah.
Yeah, the 0-point energies.
Yeah, I'll just show two slides maybe.
Yeah. You will need to go full screen also, but you can do that later.
Yeah.
Yes, sir, I am admitting. Yes, sir, I am admitting. Sir.
Good.
Okay, sir, I'll accept all this. Do you want to?
So we have another few minutes, about 3 minutes, I would think.
So in Tirupati, is that Hari was there?
Yeah, Hari.
Someone looks like Hari.
No, Hari may be in the meeting. I don't know. He certainly knows about your lecture series. And Hari, are you there? Yeah, I think there are several participants from across the country, and it's always a delight to see some familiar names and faces at these video conference meetings. And there are some new persons who we may not have met, but I hope that I will have an opportunity to get to know others as well in due course of time. Everybody is very welcome to write to us. We have another 2 minutes countdown. So we had a very nice session yesterday and some questions, answers, and so on. Yeah.
They are good questions.
Yes, indeed. Sanjay, have you met Devashish Mandal from IIT Tirupati? That's Devashish here.
Hello, Professor.
Yeah.
Hello.
Good morning.
Good morning.
So Devashish is a theoretical chemist, quantum chemistry, statistical mechanics.
Now something written on the board, whiteboard in Bengali.
Yeah. Yes. Thank you.
Information theory, and so that is, he has expertise in a large number of areas. So
Thank you.
So,
Nice to meet you, Professor Majumdar.
Nice to meet you.
so I think it is time, 10 o'clock. So I would like to begin the session. So Sanjay, is it okay to start? Are we ready?
Yeah, I'll start sharing.
Yeah. So good morning, everybody. And a very hearty welcome for the second day's lecture by Professor Sanjay Majumdar on quantum optics. We had a great session, a wonderful beginning for the course yesterday. There were a good number of questions, very nice questions, which I'm sure helped those who asked and also those who were participating, because it led to discussions which were very enlightening. So uh, I remember participants were interested in knowing how this creation and destruction operator for a photon translates into experiments. And Sanjay will be covering that in due course of time in this lecture course when he talks about uh, cavity quantum electrodynamics and the James Cumming model and so on. So all these things are coming, all the details are coming. So hold on. And today, let me also welcome Dr. Devashish Mandal, who is assisting us with the event this morning. So thank you, Devashish, and welcome to the meeting.
Thank you, sir.
And I think with that, let me request Sanjay to begin his lecture, his second lecture today. Sanjay.
Thank you. Thank you. Good morning, everyone. It's a nice morning. It's pleasant here in Kharagpur. So I think we had a very good discussion after the class on about the zero point energy. So I just want to share 2 more slides on that. So at least it can give you some flavor, may not be the depth of this, okay, which will require some extra time or extra meeting for discussion, okay. So if you see from a example of a famous example of a particle in a box in one dimension, okay, let's say. So we all know that the equation, okay, if you consider the particle in the potential is zero in that vicinity of the inside the box, okay, then you will have that if you just solve that eigenvalue equation of Schrodinger equation, and what you will get, you get the down the energies are like that, quantized energies, okay, and putting n equal to 1, okay, what you will get, the ground state energy is h cross square by 8 pi L. So this is not h, sorry, h square by 8 m L square. Okay. Now it's okay.
Sir,
Sorry.
sir, I don't think the slides are visible in full screen.
Okay, let me see that.
So just give swap display, sir. On top, swap display is there. No? Just give that once.
Swapping. Okay, don't worry. Okay.
Next.
Swap display will do. Oh,
Yes.
okay.
Yeah, now it's fine.
Awesome.
Yeah.
Thank you.
Thank you.
Right. So yeah, now I also see clearly because it was very short fonts. Okay. So ground state energies for this case one dimension box. Okay. H square by h is the Planck constant by 8 m is the mass of the particle. Okay, and L is the extent of the box. Okay. Now we can. This is what we got it from the solving the Schrodinger equations. Okay. Now, if we just try to understand from the de Broglie relations, and what it says the relation between that momentum and wavelength. Okay, so that is the wave particle nature relation. So momentum is h by lambda, and here lambda actually, if you see for ground state, is a like a Gaussian shape. Half of the lambda is filling up the box. So that means that what you can say that the particle will be available at the ground state also in the vicinity of the full length of L. So what we can say that for that maximum value of x will be L, and this maximum x actually you can convert to the for lambda. Okay, if you see the wave function, so that will be lambda will be 2L. So according to the de Broglie's relation, the minimum value of the momentum, which you can write h by 2L. Okay, so I believe you understood that. So once you have the minimum value of the energies, and as you see, the only energy, okay, so only contribution in the energy is coming from the kinetic part. Okay, so what you can say that minimum value of energy will be P square by 2m. So here, if I write that, if I replace this P by H by 2L, what we'll get, we'll get, the, sorry, I think I got it. Okay, let me, I got next page. So, we get H square by 8 ml square, same as what you got it from Schrodinger equation. So what you see that we can get the same minimum energy values from the de Broglie relation, and this is the one which is known as the 0 point energy, and the energy which is actually is available even at the ground state. Okay, and what we calculated from the de Broglie relations. Okay, so now suppose you consider two particles instead of one particle, two identical particle. Okay, let's say they are bosonic. Okay, so they both of them can be sitting inside the box. And if you think they are not interacting, so they are independent, what would happen that you will get the two equation for each of them, and you will get two ground state for each of them. So what you would have that 0 point energy total system will be just additive. Okay. But in the fermionic system, fermionic case, okay, it is not true. Because if you have an identical particle, you can't have the more than one particle in the same state. So you have to have some Pauli's exclusion principles to be satisfied, so that one particle will be ground state, another particle will be in the excited state. And that is the way actually it happens in the atoms also. Now, next, what I would like to just show you, if you just try to understand this from the Heisenberg uncertainty principle. So just look at that what I said, the maximum value of this uncertainty in the position, okay, so that will be L, okay. So what would happen that, so if you rely on the uncertainty relation, that delta X, delta P equal to H cross by 2L for the ground state, okay, then that is the minimum uncertainty limit, okay. So what would happen is the minimum value of the uncertainty in the momentum will be H cross, here remember it is H cross, not H cross by 2L. Okay. So what you can just derive from this one is that the minimum value of the energies, as we say that only kinetic energy contributes, okay, it is you are replacing the momentum by H cross by 2L in P square by 2M expressions. And what you get a different values. Okay, you get that if you just replace H cross by H, the Planck constant, which we have used in the earlier case. Okay, you get some H square by 32 pi square ml square. So what is the conclusion? Conclusion is that on the uncertainty relation, you don't get that exact 0 point energy, but what you can get some order of estimation. Okay, so it can only provide the order of estimation that what will be the 0 point energies. And if you want to know further about this, okay, there is a very good article available in Scientific American. So where actually I would like to advocate you to go through. There's not many equations, or may not be any equations there. Okay, but it explains the physical part very nicely. So I believe with that, actually, I would like to proceed. Okay, so if there is a question, I may be able to answer or try to answer in the end of this. Okay. Now let's go back to our slides. Okay, where actually we discuss. Okay, that if you have a harmonic oscillator, okay, a quantum harmonic oscillator. So the quantized energies, okay, what we got it is the n plus half h cross omega, and n is an eigenvalues of the number operator. Okay, so it actually tells which energy levels you are. And what we found out that if you are at the ground state, okay, and if you measure that uncertainty in the position and momentum, okay, you will get, okay, both of the quantities, okay, will be same. It will be the variance will be, okay, half in the unit of h cross. Okay, so that means that you have a standard deviation you can just talk about, then it will be square root of h cross by 2. So for both the position and momentum have same kind of uncertainty, same uncertainty. Okay, and if you multiply them, it satisfies the Heisenberg uncertainty relations, and that will be at the minimum level. So what you can see that if you work in a ground state, okay, of any systems, okay, you will be able to make the system such that it is a minimum dispersive state. So it will be always advised to work with the minimum dispersive state so that, okay, you can keep the systems as it is for a long time. Okay. So that was the reason that this is our high demand. But as you see that these are the actually ground state. Okay. So we'll see that later. What is the disadvantage? What is not so good if you use only in the ground state. Okay. So so one more thing I want to emphasize. I will tell again. So though I'm saying it is ground state, it is not a vacuum state for a harmonic oscillator. So I'll discuss further with the comparison with the electromagnetic field. So what is advantage of using this one? It will be very useful for communication. So if you can keep your this ground state system, okay, and you want to communicate some information through this, okay, it will be kept, or it will be what we'll see talk in the terms of coherency. It will be there for a long time. Okay. Also, it is known as minimum uncertain state. Okay. So it satisfies the minimum uncertainty relations. For a check, okay, what you can do that as you see that ground state of the harmonic oscillator is Gaussian, so just take that Gaussian wave packet at, let's say, time t, and this will be your wave functions. Okay, so if you have this wave function, what you can do that you can check that whether using this function you can see the spread or uncertainty in position and momentum, and whether that satisfies your minimum uncertainty relation, or what you can say that this Gaussian wave packet is a minimum uncertainty state or not. So what we got it? We got that that both position and momentum uncertainties, okay, at ground state is if you put back all those scaling factor which we have done earlier. So it will be h cross by twice m omega, and delta p will be square root of h cross m omega by 2. Now, so what we got it here? So because of the quantum uncertainty, okay, we got our Heisenberg uncertainty, okay, which is named by Heisenberg, okay. So we got some kind of fluctuation in both position and momentum. So this is only available in the quantum scenario. So it's called quantum fluctuation. So this is in a very small scale, okay. So that here at the ground level, also when the particle is at the ground state, okay, Unlike classical case, okay, you will have both the deviation from the classical scenario. You will have that position uncertainty as well as momentum uncertainty, and both will be at their minimum level. So as you see that both is okay. If you just tell that what is the minimum limit, this is the minimum limit of the position and uncertainty. So one point which I was trying to mention earlier also, here ground state and particle, ground state of particle in the simple harmonic oscillator, that means that nothing is there. Particle is still there, isn't it? So that if you take that mean density or okay, density of number of particles, okay, so it will be same, okay, as one. Okay, if you are started with the one particle in a harmonic oscillator. Okay. So here it is not a vacuum; it has a particle. Okay, so if you just take that number of particle in the ground state, it will be one. Even in excited state, it will be one. Okay. So here that is a difference. So you just put your that particle from ground state to excited state, pumping energy to the system or to the particle and go to the excited state. Okay. Here, like if you can think about that electron in a harmonic oscillator, so you can't destroy or create the electron just by like that. Okay, it is actually that you have to keep the lepton number conserved. Okay. So that lepton, like in atomic cases, what happens goes from one state to another state. Here also it goes from one state to another state. Now, let us see that in case of light, what happened. As you know that, okay, light is the electromagnetic radiation, or some people say that electromagnetic waves. So this wave nature is there. And in terms of field theory, okay, some people love to say that is the electromagnetic field. So whatever it is, but people are very happy to explain this light, okay, using classical electromagnetic theory, okay, that is the Maxwell's equation. It actually explains everything, whatever the phenomena was observed in the nature. So we know that we can have the different modes. So let's say that we are choosing particular mode, nth mode, or free electric field, okay, and we can get the solution from the Maxwell equation. Okay, so that solution, if we just consider, okay, so here the bold letters, they are actually designated as a vector quantity. So you have that electric field at a different position and time. What you can write, okay, since a vector quantity, okay, you can write in terms of small epsilon, okay, kind of notation, which actually designates its polarization. Okay, so direction of the field. Okay, then what we can write it that we can have the amplitude of the field. Okay, capital epsilon will tell you that what is the amplitude. It is a complex quantities. Okay, it can be written in the complex, the real part and complex part of it. Okay, so it is a complex quantities which tells about what is the amplitude. Square of this quantity will say that what is the intensity, okay, of light. Okay, and there will be waveform of this, plane waveform of this. Okay, where actually you know that from the dispersion relation, okay, that k and omega are related, and this for particular mode L until they can relate. So what you see that if you given a particular mode, okay, of electric field, what you can designate that with the L and polarization terms epsilon L, okay, for a monochromatic case, okay. So monochromatic is a particular value of omega frequency. Okay. So here, as you see that we have, we could take that complex conjugate with that, okay, which will tell that the other direction of the wave, okay, or other propagation direction of the wave. Now, if we consider the Ampere's law and put this electric field in the Ampere's law, what we can derive, you can derive that. I'm not deriving, but keeping it as for the assignment. and easy to derive. Most of you have done it already. So you can just find out the magnetic field, okay, at different position and time, and which is nothing but, okay, if you see that this will be perpendicular to the direction of the propagation, that is scale, and perpendicular to the polarization directions. Okay, but what will be interesting that in the strength of the magnetic field, as you see that there is a omega L sitting in the denominator, it will be 1 upon C times compared to the electric field if you compare. Okay, so what you can just calculate or derive that, you can derive the magnetic field from the expression of the electric field using Ampere's law. So using Faraday's laws now, okay, what you can do, that you can find that wave equation form of the amplitude of this electric field. Okay, so this is where second order in time derivative. Okay, and which will give you minus omega L square times the amplitude of one particular length. So mind that what we are just talking about, the particular mode of the electromagnetic field, that L. We can analyze this later on. So we will have that all the modes will be available. So that is not necessary at present. Let us discuss for particular mode. So what we got it? We got the wave equation for this electric field amplitudes. Okay, that L. Now, what we can do, we can just make this second order of time derivative as expressed as a two first order differential equation of time. Okay, and there'll be equations which will be, okay, I'll show it later. I think so. You'll see this first order differential equation. Okay, with the plus minus omega L. Okay. So that I am choosing the minus here, that is I am choosing that propagation along the cave, that the wave is propagating along cave directions. Okay, so that's why I just use minus sign and try to see the solution, okay, of this equation. Okay, now if you see the solution, okay, so solution will be, okay, I'll show that later, but before that what I do, I just try to make this equation, okay, that first order differential equation with respect to time as a dimensionless. Okay, so that if you want to make it dimensionless using this expression, okay, where we are putting a p factor with alpha. Alpha is the dimensionless quantities, and whatever the dimension you have in the electric field, okay, so that amplitude part, it will go in the n. Okay, so that if I just write this one, what you will get, you will be able to modify this equation for first order equation for alpha, and what you'll find that here, if we write that, since as I said, that amplitude of the electric field is complex quantities, which we can write in terms of real part and complex part. Similarly, that I can say same thing for the alpha, which is a dimensionless electric field amplitude, you can say, and that also has a real part and complex part. So let us assign this real part is QL and imaginary part is PL. So if we assign this, okay, real part and imaginary part as a QL and PL, what you can see that we can write the dimensionless variable of the electric field, that is alpha L, is just the square root of 1 upon 2h cos QL plus IPL. Now, why I am doing all those things? That's because I have some intention. So there are a lot of mathematics gone in. So please bear with me. So you will get that why all those jargons, all those nomenclatures, all those transformations are required within a few minutes. Okay. So if we just write that in electromagnetic field energy, okay, it goes by A square plus C square V square. And as you know that, so you can make this, because of C square is present, both of them are almost contributing same to the electromagnetic energy. Okay, so you can approximate that this is doubled of the electric field contribution. So half factor will go up, and you can write that this epsilon naught of integration of A square over the volume. Here, volume is a very important quantity. Okay, as I'll come to that. Okay, so here we are integrating the electric field squares over the volume to get the energies. And once you do that, okay, as we see that electric field, we can write in terms of the electric field amplitudes, polarization terms, and along with that, we can write it as the plane wave part, which will be cancelled when you do E square. So ultimately, this whole thing will be boiling down, considering that electric field in a small vicinity of the space. Okay, so what we are talking about, we are talking about that small space of volume. Okay, and considering the electric field will be uniform in that space. Okay, so what we can say that then we will have that this will be that telling you the what is the strength of the electric field, and we can get a factor which is dimensionless and variable. So it is alpha L square quantity. So what we approximate that electromagnetic energy in the small vicinity of the volume, that this is like this expression. So that is a good advantage in the sense that you see that we are just trying to make this kind of a vicinity. Okay, so where actually you consider the electromagnetic field is confined inside the box. Okay, and the box surface are actually insulator kind of things, so they can't allow the light to go out, or they can't allow light to come inside. So it is like that insulating photonic insulator kind of things. Okay, so if you just confine the electromagnetic field in the small vicinities, okay, you will be able to write this expression. And from there, what we can see that, as we have noted that alpha t we are writing in terms of qi and pi, so that here that electromagnetic energies now we are able to write in the form of q square and p square, where q and p are nothing but real quantity and imaginary quantity of the alpha L. Okay, so now I believe you are trying to get some hints why we are doing all those derivations. That is because if you just remember your earlier last class, okay, where actually we are discussing simple harmonic oscillator, you have got this in the energy terms. Okay, you have got that kinetic energy terms, which is p square by 2m, and you have that potential energy terms, which is goes by x square or q square. Okay, so that is position square. Okay. So we are trying to make an analogy with that. Okay, with the simple harmonic oscillator. Okay, and we see that it will be kind of a, we can get almost one-to-one relation between these. So here you remember that when you write the energies, okay, so alpha L, okay, this is a dimensionless quantity. So whatever the energy dimension, it should go inside this. So that means, okay, if you are talking about that light, which is actually of a photon, which we'll be talking about later, okay, so which has, as we know that we can write in terms of the frequency of the particular mode L, okay, so it will be h cross omega L. So these will go with the h cross omega L. Okay, so let me give an assignments that once you know that, okay, so this whatever you saw that this energy, if you got it in terms of this one, that means that you can write that Hamiltonian in terms of the QL and PL. So what you can do that, like the case for harmonic oscillator, we can use the Hamilton equations, okay, for this canonically conjugate coordinates of variables, okay, and get the solutions, okay. So that will be time derivative terms, the time derivative equations you will get, and from that you will get solutions. Now let's come back to that. If we now, the way we have done in the harmonic oscillator, we now will be able to do it in the case of light also, when you want to want to work in the quantum framework. Okay. So as you remember that there also what we did, we have just converted the canonically conjugate variables in terms of the canonically conjugate operators. Here also what we'll do, okay, though that hat is not there for showing the operator, but you can just take it as an operator form, so that all those classical canonically conjugate variables are converted to the operators. Okay, so it's just like a simple harmonic oscillator. Okay, so you can say that it's a canonical quantization where these QL and PL, okay, are the canonically conjugate operators. Okay, and so we can have the relation between this commutative relation between this IH cross. So once you have that, what you can write that your total Hamiltonian, which you saw it as in terms of energies, okay, okay, and we can write it in that Hamiltonian in the expressed we can in terms of the QL and PL. So once we have expressed in terms of QL and PL, which are canonically conjugate quantities, so same treatment we'll do as we have done harmonic oscillator. We can have now, okay, that some kind of operator which is we can express as Qi plus IPi. So as you remember that Qi and Pi are the real and imaginary part of the alpha L. So once you just combine them up, okay, we'll get back alpha L itself as an operator. So what would happen that annihilation operator, what we defined in the harmonic oscillator case, okay, also can be defined, okay, here in the case of light, but it will actually represent that the dimensionless parameter operator, the alpha L. Okay. So in this case, the creation operator will be just that you have to put a dagger there so that transpose and complex conjugate. Okay, so what would happen that you will have that it will be QL minus IPL. Okay, and because QL and PL are actually your they are actually Hermitian quantities. Okay, and what you will get ultimately, it is actually representing the complex conjugate part of the alpha operator. So what we got it. So in the analogy of the simple harmonic oscillator, we will be able to quantize that electromagnetic field or the light. Okay. Only thing, if you just have to remember, we have to consider a small vicinity where the electromagnetic field is uniform. Okay. So vicinity is very important here. Okay. You have to confine your space. Okay. So what we could do it now, I believe you have understood that we did that the creation and annihilation operator, okay, as we have got it for harmonic oscillator here also. But there's a difference here, which I'll come to that. Okay. But now if you do want to do the commutative relation between the A and A dagger, as you know that we have considered the commutative relation between the Q and P with IH cos, you can just check it. Okay, now it will be 1. Okay. So here is that the two different quantizations. Second quantization we have performed. One is in a simple harmonic oscillator, one is a light. What will be the difference? So as you see that when you wrote it, the energy, okay, you wrote it in terms of Q square. So, and that energies you can write in terms of creation and annihilation operator, which we will be able to, I'll show you in terms of number operator. And the energies in both the cases will be able to write in terms of the n plus half h cross omega. Yes, n plus half h cross omega. But here we are talking about that particular mode. Okay. We are talking about particular mode, that nth mode. Okay. Secondly, what is the meaning of the n here, numbers? Okay. These are the excitation modes. Okay. So that means that particle can gain the energies or lose the energies. And by the way, they can gain from one state to another state. So for that, what would happen that particle has to gain or lose the energy from outside, okay, and go from one state to another state. But here, what happened that since I know that that H cross omega L is the energy of each photon, what would happen that this n plus half, okay, here the n represent, okay, that the energy level of the particular state, okay, nth state. So if we just see that compared to that n equal to 0, so the energy of the particular nth state is n times of H cross L. That means since I say that each particle, each photon has energy H cross omega L, that means we can accommodate n number of photons there. So here the representation is different. Representation is saying that if you increase the excited state, you will increase the number of photons. Okay. So if you go to the n state to n plus 1 state, so you are increasing one number of photons. Okay. So here that is the difference between these two. Okay. So that is because the one statement which I told that here when you talk about simple harmonic oscillator particles, let's say that particle like electron, okay, we can't destroy or create like anything. But here, what you will see that is in a nonlinear process, okay, it is possible, okay. So many of you know that either in the nonlinear crystals or field theory, we can have that creation of the photons and destroying of the photons. So here, that is the advantage, okay. So in a small cavity, okay, you can have the defined modes, okay. Now you will say that, okay, so the small space, what you have the volume, where you have that different states, one state is having n, another state n plus 1. So is it all possible? Yeah, it is all of them are possible, only thing that probability of all the states are different. So that will be, I'll come to that. Okay, so how the eigenstate looks like. So if we just plot them, the eigenstate and the square of the eigenstates, okay. So so they will be same as in both the cases. Okay. So here what happened that what we are saying that parameters of the mode are defined. Here the modes are defined by the volume. What is the sizes, length, height, breadth of the volume we are talking about? Where actually you can't find the light. That will tell you, since as I said that these will give you the what is the energy of the photon. So if you change the volume, okay, you will change the frequency. Okay. So even if whatever intensity of light is there, okay, whatever the strength of the electromagnetic field is there, okay, by changing the volume, you can control the frequency or other way to say the wavelength of the light. Okay, that's one of the biggest advantage of confining the light. And what you see that you will not only get that the photon, the particle feature, you also get the controlling of them. Okay. We'll come to that later when we discuss a different experiment. So what is the motivation there in both the cases? Here, what happened? We know that there is a particle. Okay. So now putting them in the either box or in the harmonic oscillator, what we are trying to see that wave nature of them. Whereas here, we know electromagnetic field is there. But confining them inside a small box, we are trying to see that particle nature. Okay. So what is the importance? Importance is that, okay, what we can control here, okay, putting in the small potential, okay, we can control that transition frequency. And what we can control here, we can control that energy of the photons, or frequency of the photons. Okay. So that's a very important. So here, if you remember that, here we are, I'll come to that when we are talking about that inside the cavity. Okay. We are controlling the transition from one state to another, whether it's possible or not. Okay. So it's not always possible if you confine the particle or atom inside a small vicinity. So I believe you have now got a fair idea that what will be the distinction between the quantization of the light and what is the compared to what you have done or what you have gone through when you did the quantization on the simple harmonic oscillator. So these are the things which we have gone now. We have understood that we could write that in the case of the also electromagnetic field or light, that we could write that creation and alienation operator, who actually obeys the commutator relations, okay, like in the commutator relation with A and omega is 1, and you can write them in terms of the real and complex part of alpha L. Okay. Now, so as you saw that we could write the Hamiltonian, I just told April that we could write the Hamiltonian in terms of eta A, which you can write in the terms of the number operator form, okay, and get that eigenvalue of this, okay. Since we have already discussed for harmonic oscillator, I don't want to go through it once again, okay. So you can get the eigenvalue of the number operator in, will tell you that particular modes energies, okay. So here also we'll get in the h cos omega n plus half, okay. So here n goes to 0, 1, 2, 3 like the earlier cases. Okay. So these states, okay, that you saw that that defined state designated with the n equal to 0, 1, 2, 3, and it goes to infinite, isn't it? So these states, they are the actually, if you name them, okay, that eigenstate corresponding to that Hamiltonian as a phi n, or if you name them as a n, okay, state n, okay. So these n, since actually they are the eigenstate of the Hamiltonian, okay, we can form them as an element of the basis, okay. So we can create a basis set, okay, using this number state. What we call, these are the number state, also popularly known as a Fock state. So Fock states are nothing but the number states, okay. So we can get a basis, okay, using that. So what would happen that if you confine the electromagnetic field, okay, and what you will get that you will get different level of energies, okay. You have a zero number state, first number state, second number state, and zero number state means that there's no photon. The first one number state means that the single photon. Two number states are the means that there's two number of photons. So and they are actually equally spaced as the frequency of the photon or energy of the photons are same in that vicinity. So here also what you can do that you can use the creation operator on that number state and get that go to the excited state. That means you are just increasing one number of photon in the state, okay. So you will go to the excited state. So in that way, if you want to go from a particular state to another particular state, you can either use that creation operator or you can use the annihilation operator. So by using creation and annihilation operator, you can go to the higher.
So I think there are some questions in the chat box.
Yeah.
So the first one is, please explain the degenerate and non-degenerate levels for light and simple harmonic oscillator is the first question.
Okay. So okay. So so as you see that if you consider particular mode, you see the particular mode where we are taking L. Okay. You see that here you have that zero state. The energy is if you put n equal to 0, it is half h plus omega. If you put first excited state, it will be just 1 plus half means 3 by 2 h plus omega. So all these states are non-degenerate. And they are equally spaced with the energy of the photon. Okay. So here, okay, you can say that the photons which are, let's say that second excited state. Okay, so there are two number of photons. They will be designed, but both of them will have the same wave function. So you don't get the defined state. Okay, so you will get same state. Okay, so in that term of the defined state, okay, there is no degeneracy there. Okay, so in this case there is no degeneracy. Okay, I think that's the answer to the question. But
so,
if you have different modes, okay, certainly there will be. Yeah, sorry.
So there are a few more questions. If you'd like to address them now.
Okay.
So the first one is, how can light photon be destroyed?
Okay. So we'll come to that. Okay. So in the subsequent discussions, okay, the nonlinear process, as I said, okay, the second harmonic generations, okay, or there is the as we'll talk about vacuum fluctuation, where you can have this many number of photons can created or annihilated, okay. So you'll understand that the like a second, I think you know the second harmonic generations, okay. I'll also come to that, okay. From there, what would happen? Okay, you can have that a photon having energy or frequency of twice omega can go to a two photon having each of them having either omega or the addition, that energy addition will be same as the parent photon. Okay, so there are the possibilities, but that is these are all nonlinear process which is possible. Yes.
So the next question is, does applying the annihilation operator on the ground state of a photon really destroy the photon?
I'll come to that. Very good question, but I'll come to that. Okay. Any other question?
Okay.
I'll take up at the end, because that is a very good question. Okay. That requires some
Okay,
explanation.
so there are a few more questions, but if you want, you can take them up at the end.
Because I have, I think, 10 to 12 minutes. I just want to
Okay.
finish and then answer. Thank you. So the advantage of having so many states, okay, is so as I said that from one state to another state, okay, you can go using the creation and annihilation operator, okay. So what you see is it here, okay. So if you just go from, let's say that if you come from the ground state to the excited state, the nth state, you have to operate the A dagger in times, okay, as is in the harmonic oscillator. Okay, so you operate in times and get it. Now, what is possible is that once you have that your any particular electromagnetic states, if you want to define psi, so using that because you are in the Hilbert space, okay. So what we can do that we can have that we can express that part any arbitrary states of the light, okay, can be expressed in terms of that basis. Okay, that basis is okay. It will go from n equal 0, 1, 2 to infinity. So we can sum over them, okay, of the n states, okay, and get that this is a coefficient of the expansion, okay, and get the psi. Okay, so any arbitrary state of the light can be created as a mathematically, okay, using this expressions. What does it mean? Means that what you have got it now, okay, you can write that expression in terms of a dagger to the power n, okay, and the prefactor is there. And the I want to exploit on this idea in the new things, okay. So here is the coming what is actually the actual quantum scenario of the light or electromagnetic fields coming through the hands of the Roy Glaber. Okay. So far what we have known that we have already known all those things. So we have creation annihilation operator. Okay, we have number of states. Okay. So yeah, here is the one of the questions which was asked in between. Okay, what would happen? Okay, when you annihilate subsequently, and let's say you annihilate the first one number state first. Let's say one number state. What you will get? You will get the zero state. Okay, zero number state. Okay. So that means here you are saying that there is no photon is there. But these are, remember, these are all relative. Okay, relative statement. So compared to the, so if you assign this is the no photon, it is giving you single photon. In another state will give it in number of photon. So it is compared to that zero state. Okay. Now if you just annihilate that zero state again, what you will get? You will get the zero eigenvalue here with the vector, the zero state. So that actually, once you operate an initial operator on this ground state of this light, okay, that is a zeroth state, okay, you will get null vector. So that is actually, literally, it is called null, okay. So if you want to know further about this, There's a very nice description in the J.J. Sakura's books of modern quantum mechanics. Okay, so you just maybe have to look at it. Okay, because it actually requires a very detailed explanation of this. I just want to avoid it. So here, okay, you can define your vacuum, okay, or null vector by saying that you are applying the annihilation operator on the zero state. Okay, so but so that is what I said. Okay. So maybe I can discuss about the questions again after this is, session is over. Okay, I'll come back to that as answer to that question which was asked. Okay. Now I want to just discuss that. So what we saw it that uh, by using creation and annihilation operator, you go from one state to another state. And what we also know that each of the photon having energy h plus omega L. What about the momentum? If you see that momentums of the particle, okay, so which you also can write in terms of electromagnetic theory, okay, that cross product of the electric field and magnetic field, okay. So what you will get that if you just replace that expression which you have discussed, okay, of electric and magnetic field, you will get nothing but h cross k L alpha L square. And as you know that alpha S square, okay, alpha L square, we can write in terms of A dagger and A. So what would happen that these momentum operator, okay, we can write, okay, operate on the number state, and what we'll get the h plus k as a factor coming out with the n as a eigenvalue, okay, for the nth state. What does it say? It says that, so what you see the nth state, okay, if you look at nth state, okay, its momentum, since we are operating momentum operator, is n times of h cross k. It's just like that way we have got it for the energy, okay. So all the photons will have same momentum h cross k. So here just k, the L suffix has dropped, okay, but we should keep it, okay. So this is meant for the particular mode, okay. So both in the case of energy and momentum, L suffixes are dropped, but that is for generality, okay. But you have to keep in mind that this is for the particular mode. So what we got it in the number state, which actually represent the n number of photons, okay. So it actually says that each photon having the same energy h cross omega L and same momentum, okay, h cross k L. Now, interesting point is that, okay, so once you know that electric field, okay, which we wrote it in terms of alpha L, okay, the dimensional is operator of form, okay, and which alpha L we can write in terms of canonically conjugate operator, that is P and Q. So if we just can do that, okay, and what you will, this is, I can keep it as an assignment, okay, what you'll see that electric field operator also you will be able to write in terms of that P and Q operator, okay, and you have this strength of this is coming as in the front. Now, what would happen if just calculate that expectation value of the variance of this electric field operator with respect to vacuum? What you will see that you will get nothing but the strength part of the electric field. Okay, so that is n square. And this I know from this earlier statement. This is goes as a energy dimension. And if you just compare with the earlier expression, this is nothing but h cross omega by twice epsilon v. This is for particular mode VL. Okay, so VL is as I said, and this is will be omega L. Okay. What does it mean? It means that these is, if you see that h cross omega L is the energy of single photon. in that volume V. So if you confine the electromagnetic field, a light inside a small volume VL or V, okay, so what would happen that fluctuation of the electric field, okay, will be of the order of 1 photon energy. Will be of the order. So what you see that quantum fluctuation, what you see it, okay, at the level of vacuum, okay. So you can get the fluctuation at excited states also. You can calculate the same expression in the excited state. But what we are now talking about, okay, that if we just talk about the quantum fluctuation of the electric field at the vacuum, okay, that is actually represent 1 photon electric field. Okay. So that is a very, very, very strong statement. Okay. So you could quantize, okay, you could quantize the fluctuation. So either the energy, what we just said that vacuum, the null vector, okay, so which we got it by operating annihilation operator or the zero state, ground state, okay. And now that we got here that we are saying there is some energy left, okay, and which actually we saw in terms of the harmonic oscillator and here also that H cross omega, okay, which you can, okay, understand as a single photon, okay. So that fluctuation, the quantum fluctuation, you can understand as a single photon electric field, okay, which is actually going up and down. So you can have half H cross omega above the energy, you can go the half H cross omega below the energies, the ground state, okay. So that is a 1 times H cross omega. So ultimately that is the total fluctuation will give you the 1 photon energies. So what happened that, so I don't have much time, sorry. So just I want to conclude this session. So that this fluctuation, what you saw it, okay, are just coming from the variance of the canonically conjugate operator Q and P. So from the uncertain relations, okay, you will be able to explain this quantum fluctuations, okay. And what also important is that here at that ground level, okay, what you see that fluctuation of the canonically conjugate variable Q, that is real part of the alpha A, remember, that actually is same as the imaginary part of the alpha A. Okay, that is, so all are operator form, okay, hat is there, okay. So if we just write them, okay, the delta Q and delta P, both of them are same here also. It is H, just like a harmonic oscillator, H cross by 2, okay. So, and it obeys the minimum uncertain relations. So here also, what would happen that, okay, at that ground level, that where there is we are saying that 0 photon level, okay, that level also satisfies the minimum uncertain relations, okay. Both the canonically conjugate operator Q and P, their uncertainties or their variations, okay, they actually are same, okay, and that is at the minimum level. So that's why this ground state of the light, okay, also known as minimum uncertainty state. Okay. So that's as a very useful, and this fluctuation what we talked about at the vacuum state, okay, can be understood as a lamp shift, which you may have heard about that, and that is in the case of the hydrogen atom, okay. So and which will give you the you remove the degeneracy of the p states, okay, or orbital angular momentum degeneracies, okay. So that actually is a benchmark for the quantum electromagnetic effect. So I'm just maybe I'm just naming many of the words, okay, which may not going through for to all of you, but things that I'll explain maybe in the question and answer session, few of them, okay. That this is one of the things which actually is really interesting. Maybe if you don't get it from the discussion here, you just look at the books, As I said, that you can look at Sakurai's books or any other books of classical or not the quantum mechanics books, okay, and you can clear your ideas. But these are very important. I think I just want to end it that what we achieved it, or that we have achieved that the vacuum state as a minimum dispersion state, a minimum uncertain state, okay, and details of this one, whatever is discussed, okay, you will be able to get it in this book very, very nicely, okay, by Greenbaum aspect and Febre's books, okay. And so the soft copy may be available somewhere, or we can just hand on the hard copy in the library. So that will be very handful for you. Understand? I think thanks to I want to stop it here because time is over. Okay. So I'll be love to answer questions and answers. Some of the questions. Yes.
Okay. So
After 5 minutes, I'll call you again. So,
Sorry. Is there any question?
yes. Thank you, Professor Majumdar. It was a wonderful session.
Thank
So
you.
we have now a few questions in the chat box. So first we will follow these things, and later, if time permits, so we will take few more
Okay.
from the audience. So first question was asked by Pooja. That please explain the degenerate and non-degenerate levels for light and SHO, simple
Yeah.
harmonic oscillator.
Yeah. So if you, yeah, that was the question earlier you mentioned. Okay. So as I explained, okay, let me see the way I can go back. Yeah. So as I explained from this picture, okay, so that you have the different states, okay, in the harmonic oscillator, okay. Let's say that it is not for the light, it is for the harmonic oscillator. So you have that single particle, okay, so which can be in the ground state or excited state or further excited state. Here, there is no degeneracy. There is no degeneracy at all. Okay. But when you talk about the light, okay, so what would happen since we are talking about that these states are actually occupied by a defined number of the photons, okay, so there will be degeneracy at different levels, okay. So that here in the ground state, no photons are there. So these are all actually what the statement which will be clear in the next class also, that we are just talking about relative. Okay, that is a vacuum. Okay, vacuum actually has, as we have understood, okay, has all the modes. Okay, and each mode at its lowest energy level half h cross omega. Okay, so if you add them up for the infinite number of modes, you will get infinite. And this infinite energy, okay, that is summation over the all the modes, okay, of half h plus omega, is there for all the states. Since it is there all the states, we just take that that is a relative difference, okay, or what we say that here the number of photons are relative compared to the zeroth state. Okay, so what we say that the here, okay, you just don't consider that infinite energies, okay, like a voltage. We are doing the earthing of the voltage in our home. You know that when you do the electrical circuiting in the home, okay, that's because that the lump sum of the voltage goes, okay, inside the earth, okay, so that what we get that bias of the voltage. Okay, here also what we are talking about, that relative energy difference between that zero state to one state to a state. Okay, so that what we see that in the case of light, unlike the simple harmonic oscillator, will get different number of photons. So there is a degeneracy comes in the number of photons at each level. So that degeneracy you have to understand compared to simple harmonic oscillator.
Yeah. Thank you, Professor Majumdar. So I hope that explains Pooja's query. Now we have two related query, one from Girish and other from Nishita. And they ask, Girish asks that how can the light photon can be destroyed? And associated to that only, Nishita asks, does applying the annihilation operator on the ground state of a photon result in destroy the photon?
Hello.
Hello, can you hear me,
Yeah,
Professor Majumdar?
actually, I couldn't hear in between. The next question, next
Yes.
person's.
Yeah, so Nishita asks that does applying the annihilation operator on the ground state of a photon result in destroy the photon?
Hello.
Hello, can you hear me, Professor
Maybe
Majumdar?
I answered that Dr. Grish's questions.
Yes, yes, yes. Yeah. So Girish's question is, how can be light photon be destroyed?
Oh, sorry, I think I got a unstable network connection. Okay, I couldn't hear the second one. Maybe let me answer the first one, which can actually, which will be sufficient to answer for the second one also.
Sure, sure, sure.
So what is happening? So as you know that in the case of the optics, okay, you have a nonlinear process. So once you okay, I don't know whether I'll be able to show my this. Maybe let me minimize this. Okay, let me show my notebook. 1 minute. Notebook is seen.
Yes, 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 Professor.
Okay. So what happened that okay? So so suppose okay, once we have suppose on atom is there. Okay. So this is atom, and we shine the light with a frequency, let's say twice omega. So what would happen depending upon the energy levels? Okay, what would happen that if this twice omega frequency is resonant to that any transition, okay, between these energy states of the atom, so atom will get excited. So what would happen? So you have the twice omega coming in, and when it is actually decay or emit, okay, either it can decay to that directly to that state, original state, to that twice omega, or if there is any intermediate state available, okay, it can, there is a probability that it can go to that intermediate level and subsequently go to that from that level to the other. So what would have possible that you can get the omega here and omega here, or this is omega 1, this is omega 2. So what you see that, so from one photon, you could get two photons. Or other way to say, so if you put a two photon and make that transition available, and when you just emit, you get one photon. So these are the nonlinear process. Okay, that this is called second harmonic generation, if you remember. Okay, so what would happen here? What you are just able to create or annihilate the extra number of photons. So this is in chi2 level. That if you remember that the polarization expressions. So at that nonlinear chi2 level, you can have this.
Yeah, thank you, Professor. So next question was asked by Ayan Banerjee. Can you explain whether the symmetry of the volume used for confinements affect the result?
Definitely, yeah. That's a very good question. Okay. So as you saw that, what actually in the expression that we have this relation H cross omega L, okay, is equal to 2 times epsilon naught VL, okay, and you have the NL. So now what would happen that, so since the intensity or so not intensity, what you said, that is staying, let's say that the amplitude, okay, of the electric field is constant, let's say. So here this omega L is defined by the what is the volume is there. Okay. So which frequency will be able to sustain inside that small space, okay, will be dictated by this volume. So that actually very important ingredient for the confinement of the light, that you will be able to control your particular frequency. Okay.
Yeah, thank you, Professor. So next one was asked by Parthana. Actually, she had three questions. So first one is, could you please explain how can you write epsilon, that amplitude, as the product of alpha and curly n? And the second one associated to that was, what does alpha physically mean other than a mere mathematical quantity to create one-to-one correspondent with a simple harmonic oscillator?
Okay. So in the simple harmonic oscillator, actually we didn't use alpha, but here we are using alpha in the sense. So you remember in the simple harmonic oscillator, okay, we have the small q, the position, and a small momentum operator, which actually we made it dimensionless. Okay. So by using the factors square root of h cross by m omega, okay, and p case is square root of m h cross m omega by 2, okay. So using this factor, you could make dimension. Here also, when you have a light, okay, so what you could do it actually, so you got the electric field, okay, is proportional to that amplitude part, okay, of this epsilon n. And this epsilon L is amplitude. It can be complex quantities. Okay. So what would happen that now, if you want to make, actually our idea is to have an operator which is dimensionless, as you saw in the case of harmonic oscillator. That's because that we want to get that commutator relation in a very simple form, unless you want to put back all of the prefactor in the commutator relations. Okay. So as you saw that what we got it in terms of the creation annihilation operator, or in terms of Q and P, okay, is IH cross, okay. So that's because that we made the Q and P is dimensionless. And that Q and P, we got it from here is by the, if this is told as this is a 1 upon 2H cross, okay, Q plus IP, okay. So sorry, there is capital P. So using this relation, okay, making it a dimensionless, you have an advantage that you get the nice expression of the commutator relations. Okay. So here also you make the same approach by putting that these canonically conjugate quantities dimensionless. Okay. So here you see that ultimately by doing that alpha epsilon, making it dimensionless, we get the Q and P dimensionless. And so what we got it, that we got that real part of this epsilon, okay, is a Q, and imaginary part of this epsilon is capital P. So those are canonically conjugate quantities. I think this answers to his question, or her question.
Yeah, I think. Thank you, Professor Majumdar. So she had one more question, that in second quantization, using fermionic or bosonic operators, we can indeed add or remove particles. How can we say that they can't be, as mentioned in the table?
They can be in the simple harmonic oscillator.
So she is asking, how can we say that they can't be as mentioned in the table? So in your presentation, I think, yeah.
Okay. Okay. So in the table, what we did actually, we are comparing simple harmonic oscillator with the light, isn't it? So as we are just explaining, okay, that simple harmonic oscillator, when I'm talking about, is a potential is harmonic oscillator, and you have a single physical particle like electrons. Okay. Now so it's by being confining this in that harmonic oscillator, okay, in a small space, what we got it, we got defined energy levels, okay. So these are the defined energy levels, and this electron can be available in any of the energy levels. So what is the most likely in a system like this one, electron will be having more probability to sit in the ground state. But it's not that you will not get any probability that it will be in excited state. Okay. So what you can have that, you can just pump energy to the electron and it can go to from ground state to the excited state. So here, by using the second quantization, okay, we are meaning it, okay, that particle is going from one level to another level. So remember that here the second quantization in the case of the harmonic oscillator is like your like atom you can think about. Okay, there also you have the Coulombic potential. Okay, think about the hydrogen atom. You have a nuclear attraction is there. Okay, so that is you can think about harmonic oscillator. And what you can do, you can just excite the electron which is available in the hydrogen from one s2 to another state by pumping the light or by pumping the energy to the system. Okay, so here we are not destroying the particle. Here we are moving particle from one level to another level because you will not be able to destroy them. Okay, so that is a violation of conservation law, some of them. Okay, but in the case of light, okay, that is not a problem. Okay, so here that is the advantage. Okay, here what would happen that these levels, okay, whatever you saw it, this level corresponding to number of particle. Okay, so this is the relative number of particle is 0. This is relative number of particle 1. Okay, and each suppose here the photon which is available in this first excited state, okay, will have the energy h cross omega n. Similarly, a photon which is available in the second quantum state, so there will be two number of photons. Both of them will have h cross omega. So here you are able to create or destroy. Okay, in the case of the when you are confining the electromagnetic field. Okay, or confine the light. Okay. I think that's answer to your question.
Thank you, Professor. So actually, we are running a little bit out of time. So there are a few more questions, but I will take one last question, and that is from Trina. So Trina asks, why ground state energy of a particle moving in a circular ring is 0? Is it not violation of Heisenberg uncertainty principle?
See, a circular ring means you are trying to put a different structure of the potential, isn't it? So what you can do that you can just calculate. If you have a circular ring kind of things, you calculate using suppose you are having a particle here. Okay, so you calculate from the Schrodinger equation what is the ground state. Okay, and try to calculate the energy of this. Okay. So whatever the energy you will have for the ground state, that will be your base level. Okay, so you set. So it's not necessary that to be 0. Okay, so as I said for the harmonic oscillator, as I said for here in the case of light. Okay, these are all relative. So we are saying that same is like the atomic case or molecular case. These actually they are having some energies, but we are talking about everything we are talking about relative to the ground state. Setting that you can set that is the energy is 0 and then go. So but there is some energy left. Okay. So here you can calculate. Okay, you calculate the potential and then using Schrodinger equation, you calculate the ground state, find the energies. Okay, and see that what is the energy. So I don't know that what is the energy of this system, okay, at the ground level. But if you calculate and find out what is the value, if you find that it's non-zero, don't bother. So that will be the base level, okay. And what we will talk about the relative difference on the excited level compared to the base level.
Yeah, thank you, Professor Majumdar. So let me thanks once again Professor Majumdar for his wonderful presentation, and it was a very nice session today. Indeed.
Next class
Thank
we will
you,
have a
Professor.
point light, which we will discuss. So I'll come to it.
Yeah, I would also like to thank all the participants, those who are here today, and also asked so many beautiful questions. So I can tell you that those questions which was not been addressed, we will pass it to Professor Majumdar,
Yeah.
and surely you will you will get the answer. But thank you, everybody.
Thank
Now
you.
let me request Professor Deshmukh to conclude the session. Sir, Professor Deshmukh?
Is it there?
Yeah, sir is there. Yeah. Hello, sir.
Is there? Is just unmute.
Yeah, probably. Hello, sir. Sir, you have to.
Yes.
Yeah, please. Yeah.
Well, there was a little bit of technical interruption and I lost contact. I don't know if others were on air, but I lost contact for about half a minute or maybe something like that.
Yes, sir. So our session is over. So I request you
Yes.
just to put some concluding remarks for the session.
Yeah, nothing very much. I think it was a great session. Thanks to Sanjay in particular, and also to many others who are making this possible. Devashish, and we have uh, very good support from Abhek, Salvi, and many other volunteers who are taking care of the question answers. They are routing these questions to either to the speaker or to Devashish and supporting the session. So that there is a lot of background work which is being done by many volunteers and also an excellent technical team consisting of Ravi, Arun, Satish, Devi Prashanti, and many others. So very many thanks to everybody, and we will have the next lecture tomorrow morning at 10. Um, there are some questions for which we are not always able to find time. So maybe you can send these questions by email to Sanjay or to me so that I will also be happy to uh, forward these questions to Sanjay and then
So one more thing I forgot to mention that yesterday I think I sent the assignment which will be discussed tomorrow. So those who think that is some of the questions should be discussed, maybe inform us prior maybe few hours before, so that we can prepare slides for them.
Yes, yes, Professor. Thank you.
Still
Professor
have the
Deshmukh
assignment.
was having some problem.
I think my internet connection is not very stable, and so please, yeah.
No problem, Professor.
So
Okay, yeah.
yesterday I had forwarded the assignment to Sunil. So I believe that he has forwarded to others. So which will be discussed tomorrow afternoon. And I request all the participants who are actually taking the session, if they think problems are interesting and would like to be discussed, if they know us a priori, then we can prepare some slides for them. So
Yeah, sure, Professor. Yeah. Okay. So that concludes our session for the day, and thank you very much. So we'll see you tomorrow morning once again. Thank you, Professor Majumdar.
thank you.
Bye.
Bye.
Bye.